I will be presenting on performing open heart surgery on a Furby. So let's get started. So a little bit about who I am. Again, my name is Michael Coppola. I do vulnerability research, and in addition to work, I'm also finishing up my undergrad at Northeastern University in Boston. And I like to play CTF every now and then on a team called Marauders. And if you want to learn more about what I'm doing and other research that I've done, my site is poppopret.org. So first off, what is this thing? If you've never heard of a Furby, it's an animatronic toy made by a company called Hasbro. And basically, it's a little mix between an owl and a squirrel, and it's covered in colored fur, and it's really entertaining. The specific Furby model that I targeted was the 2012 version. There were older ones that didn't have all the bells and whistles that the new ones have. So this one was a lot more fun to mess with. An interesting fact about it is that it starts off speaking a gibberish language called Furbish, and then over time it's supposed to learn English and start speaking English to you. And what it does is you can do things with it. You can like pet it and it'll squawk at you, and you can make a loud noise and it'll acknowledge that you're there. And also, if you put multiple ones next to each other, they'll start talking to each other. And that's actually where a lot of the fun stuff comes in. So again, this thing communicates. Interestingly enough, the old ones used to use infrared to communicate, but the new ones use a protocol that's actually surprisingly similar to bad BIOS, and I'm not even kidding. So if you're not familiar with what bad BIOS is, basically if you've heard of a thing called the mosquito tone, teenagers like to use it for their ringtone, or basically it's a really high-pitched frequency that only young people can hear. And basically what this thing does is it actually takes that really high pulse, that high frequency, and pulses it back and forth between different devices. So there's a speaker and a microphone, and they send these data pulses back and forth. And it's really, I'm not sure why they did that, because if you're under the age of like 25, and everyone who has this it's really awful, and it's just terrible. And I was playing around with it, and my roommates were there, and they just told me to shut it off. Anyways, this isn't the focus of the talk. The communication stuff has already been cracked wide open by a guy named Ian, and he posted his results on his GitHub. And basically, he provided the ability to record the data pulses that the Furby would send out, and you can decode them into what message it's actually saying. And then also you can encode it from your computer speaker and send messages to the Furby. So what I did was more hardware stuff. Anyways, a quick look at the circuit board. You tear it apart, and you see all sorts of components everywhere. It's an interesting L shape where you have a little daughter board on the side. And on the other side is where the LCD screen was mounted for the eyes. But when you take it off, you see all sorts of components underneath it. So just a quick exercise in actually identifying components on this thing. What you're looking at here is a small EEPROM chip. And there are different ways that we can figure this out. Usually, EEPROM chips are just small, square SOIC packages, and there's 8 pins on them. If you didn't have that information, you can also see that there's a silk screen on one of the pads that says SCA, and that stands for serial data. And if you're lucky, and most of the time you are, you have actual markings on chip themselves that identify exactly what chip it is. So you just Google this, and you see, oh, it's an Atmel 24C series EEPROM chip. So that's great. We want to actually dump the contents off of this chip, so we have to desolder it from the board. There are different ways to do this. Some are better than others, some are easier than others, and some are less expensive than others. Different ways you can do it is simply just grabbing a heat gun and using tweezers. The problem with this is that the heat gun is pretty much taking like a sledgehammer, because it's just going to heat everything in the surrounding area up to a really high temperature, and you're going to burn the board. You're going to just make everything really awful. So instead, what you want to do is you want to use something like a rework station if you still want to use hot air. So I got this really cheap rework station off of SparkFun for $100. And basically, it's a heat gun that you can control the temperature of and the airflow of, and you can funnel it into a really small space. So you're not just desoldering the entire board at once. Also, you can use solder wick, which is just a braided metal that you put over solder, heat it up, and then it basically acts like a sponge and takes the solder off. Also, if you want to take all of the sides, like one side of a chip off at once, you can use a blade tip on a soldering iron, hit all of the contacts at once, wait till you hit reflow, and then just yank it off. So now that we have the chip off, we can interface with EEPROM, and this specific EEPROM used the I2C protocol, and the basics of the protocol is that there are 3 address pins, such that when you want to interface with one chip, you have to also send it its address. So what this means is that you have 3 bits that identify what address it is, so you have 2 to the 3 possible chips that you can chain together. And if you want to talk to the first chip, then you send an address of 0. If you want to talk to the 8th chip, then you send an address of binary 7. Also, you have a write protect pin, so you can pull that high or low depending on whether or not you want to enable or disable writing to it. Also, you have your clock and your data. So that's great. We dumped the EEPROM, and we see that there's a couple bytes everywhere, but mostly it's just nulls. We don't really have any idea of what this data is, but the fact, just making guesses and hunches, as most reverse engineers do, is probably something to do with settings, or because over time the Furby is supposed to actually learn things and is supposed to like interact with its environment. So if there's any need for volatile data, it's probably just for its current state. So moving on, we want to see what else is on here. We flip it over and we see this giant blob of epoxy here, and this is really annoying. And what I learned is that this is a fabrication technique called chip on board. Typically, when you have you're fabricating a printed circuit board, you usually have a chip with it's in a black epoxy package with pins coming off of it, and then you solder onto the chip on solder pads. But even cheaper, you can actually take the internal die of the chip, plant it directly on the board, and then cover it in epoxy. What this does is it is a cheaper process, but this makes it so that we don't have as much information, because now you can't print markings on top of it, and you can't see like all the pins that are coming off of it, and you can't like attach probes on there without actually slicing the traces and putting a probe on this tiny little trace coming off of it. But anyways, so we can try to make assumptions about what exactly is under here. If we look at the fact that there are tons and tons of traces coming out of here, a lot of it is probably I/O, and that's a pretty good indicator that it's actually a microcontroller. Also, if we look at the silk screen on the top right, we see that there are a bunch of references to SPI and one reference to SIP, which is probably just a typo. But anyway, if you flip it over, and we can kind of pinpoint exactly where those pads were and where the vias go up to the other layer of the board. And we can see that there are 2 other chip-on-board components there, and the SPI pads kind of come right underneath it. So either one of those is probably talking over SPI. And for the life of me, I can't really figure out why you would have chip-on-board on another little board and then solder that little board onto the big board. I guess it could be cheaper, but it's really hard to figure out why. Anyways, also we see on the left that there are 2 pads, ICE CLK and ICE SDA, which are references to clock and data. When you have a circuit board with a microcontroller or CPU, usually you have an interface called JTAG that lets you do debugging and lets you dump the contents or whatever instead of breakpoints. Other types of platforms have ICE, which stands for in-circuit emulation. So maybe these could be debug ports that we could use to gain control over the MCU. So we desolder the component on the right, and we actually find that there is a full pinout of the chip that is expecting there, and we find that it's actually SPI data, or SPI memory chip. So interfacing with SPI is very similar but kind of different from I2C. And basically, the main difference is that SPI has this concept of shift registers for communication, where you have 2 ends of you have a client and a server, or client and server, 2 sides of communication, and then in order to actually transfer data back and forth, they both have to send the contents of the registers at the same time. Usually when you're talking to a chip and responding to it, you have one side talking to the other, and then the other side responds. But the fact that you still have to send the contents of your registers at the same time means that you usually, if you're listening, you're going to fill your registers with just garbage bytes, and then when you're sending, the other side's going to send you garbage bytes just so it can receive your bytes. We have MISO and MOSI, which is master in, slave out, and master out, slave in, which is just the client server, quote unquote, connection or relationship. And then chip select, which you pull it high or low, whether or not you want to, like, quote unquote, start your session with the chip and actually interface with it. And you also have clock, write, protect, and hold. So if we want to dump the contents of the chip, I started out seeing if I could use my Arduino, but it ended up being too slow for SPI. So I went online, and off of Adafruit, I got a thing called the Bus Pirate. And Bus Pirate is great. It's like a multi-tool for all sorts of different protocol stuff. And I used a program called FlashROM that interfaces with the Bus Pirate to actually dump the contents of the chip. But the problem is that I attached all the probes on the Bus Pirate to the chip, and then I ran FlashROM, and it ran through its database and said, I don't know what this chip is. So at this point, I was like, whoa, okay. So I kept looking online, and I saw this tool on GitHub called SpyTool, which was just some guy's one-off project, and it was supposed to specifically work with the Bus Pirate. So I plugged it in and ran it, and it worked, and it returns data. But it was really interesting, and it seemed kind of erroneous. It would return data, but the same OX4000 bytes would just keep repeating over and over and over and over. And I thought that this was correct until it just didn't seem right the more that I thought about it. Because there's no point to keep repeating that data over and over if there's really no need for it. So what I did was I bought a silly knockoff logic analyzer off of eBay for $10. And it came from China, and then I put the probes on MISO, MOSI, clock, and CS, which are really the four main contacts that you actually care about if you're trying to see the communication of the data itself. So just to verify that the logic analyzer actually worked, what you see here is actually a session of master trying to read off data from an address from the slave. So it sends OX3, which is the SPI command for read. It sends a 3-byte address, and then it just starts shifting the garbage bytes to the chip because the chip is going to keep responding with the data at that address every time you shift the byte. And then when you're done reading data, you just pull chip select high, and then that ends your session. So the cool thing was, all right, SPI tool is sending SPI commands, so it's sending the right things, it's facilitating communication with the chip, but it's just sending the wrong ones. And I watched on the logic analyzer as the SPI tool read the entire address space, and then started from the beginning and read the entire address space, and this over and over and over and over. And I was like, okay, well, this program has to be buggy, so I'm going to go back and try to use FlashROM again. So again, the problem is that FlashROM can't recognize what the chip is, but maybe we can write the config and it'll let us recognize what the chip is. So what I did was I attached the logic analyzer and watched FlashROM try to probe the chip to see exactly what it is. And here you see that FlashROM is sending the byte OX9F, which is the SPI command for read identification. And then the chip is responding with its 3-byte JDEC ID. And JDEC is basically a organization that provides standards for all sorts of like digital protocols. And they maintain a database of different manufacturers, and each manufacturer can register a byte with them. So if you see here, the first byte is OXC2. And then if you just Google these 3 bytes, then you get a hit on the exact data sheet that actually matches with this chip. So with this, we can see that the chip is actually a Macronix mask-ROM chip. It's 4 megabytes, and the fact that it's mask-ROM means that it's actually read-only. Whereas Flash, you can read and write from it. Mask-ROM actually has the data that it was manufactured with burned into the chip itself. And we see that There are 16 pins total, but there were only 8 pins coming off of the chip itself, but 8 of them are disconnected internally, so it still makes sense. So here I ended up making a proper flash ROM config, and I pushed it up to the project, and now that's possible to dump from this type of chip. So now that we have this ROM, we need to see exactly what's on this. We have a 4-byte memory, 4-byte binary image, and the first thing that you always do when you pull firmware off of something is just run binwalk on it. It makes everything a lot easier. It identifies headers, and then it lets you analyze those objects further. But the problem is that binwalk said, I can't find anything here. Okay, so now the second thing that you always do in reverse engineering is just run strings on it. If you can find ASCII strings, then your day is made. There were no strings in this image. So now we're just working with raw binary. We actually need to figure out what this is. So looking at a hex dump, we see that at the very beginning there's a big blob of binary, and then there's a bunch of null padding, and then there's a second big blob of binary. And looking at the actual contents of it, we can kind of make a couple of assumptions. We see the first 4 bytes is, if we interpret that as an integer, we actually see that that number, AF6, multiplied by 4, which is the size of an int, is pointing to the end of that section of binary data. So this could be a number of entries, or if it's a header for something, it could just be a number of ints to follow it. And then if we look at the actual ints that follow that size parameter, we see that these numbers are incrementing, and they're also reasonable offsets into the file because they're all within the confines of the actual binary image size. So now looking at those actual offsets, we look at the first one, OX4000, and OX4000 is the location of the very beginning of this second binary object in this ROM. And we see that if we look at the first int at that location, it also is a size that when you add it to that location corresponds with the second offset from the header. And it keeps cascading all the way down until the very end when we find that there actually isn't a size at the beginning that corresponds to the next record. So this format holds for the first half, but then the second half we're going to have to figure out exactly what that is as well. Interestingly enough, we find, looking at the offsets, that that don't have records that have that size data format, they're actually at a constant 256 bytes away from each other. So maybe there is no need for that size parameter. So, okay, we have these records and we have this header format, but we don't know what kind of data is actually on this. Is it code? It could be a interrupt vector table, but that's just not what it looks like, and there's no reason that there would be a size parameter there. It could be audio data. It would make sense if these variable records held audio data because they're going to be variable sizes. And maybe the constant 256 byte records are image data. It would make sense since images are always going to be the same size on the LCD screen. So to confirm our hypothesis, what we can do is we can actually manipulate the data on the chip itself and then see how the system behavior changes. The problem is that mask ROM is read-only since the ROM is burned at the factory, so we can't reprogram it. So as a solution, we can just desolder the desolderable board that the chip on board is on. And what we can do is actually replace it with a flash memory chip that's both readable and writable with similar specs. And then what we do, what I did was I flashed the original ROM on there, confirmed that everything still worked fine, and then from here we can continue to fuzz the data and see exactly how the Furby will respond. So observing system behavior, first thing I did was I started from the beginning of the second binary object and clobbered everything with A's. There's A's everywhere, and what that meant was that the thing booted up fine and there was no audio. And the LCD-I still worked fine, except the image data was just all static. Instead of like eyes that looked all cute and had hearts everywhere, it was just static and looked really scary. So, cool. So that means that there's probably actual like audio and image data there. So the next thing I did was I pointed all of the offsets in the header as a second test to the first record. And what that did was that it only produced one sound. So this variable length record is probably sound because I kept repeating that one over and over and over. And again, the eyes were still just messed up because now you have your likely image pointers pointing to an audio record. So just starting out, let's start with the image data because that's more fun. We find that each record is exactly 256 bytes. And this actually makes sense because the LCD on the Furby is 64 by 32 pixels, and that equals 256 times 8. So it would be reasonable that 1 bit in this record corresponds to 1 pixel. So what I did was I just wrote a really simple, naive program that literally mapped each bit in the record to 1 pixel, just row by row. And I actually found that I got sort of valid-looking data, but it looked scrambled. So you could see like rectangles of cohesive pixels next to each other, but then they're just mixed up in the wrong order. So what I asked around and actually learned that usually LCD screens don't operate on linear data like that, and there's usually some sort of mapping to correspond the actual bits in the data to where that pixel is on the screen. So what I started off doing was I was like, okay, that's fine. I'll just flash records that have 1 or 2 pixels at a time, and then write down where that pixel was. And this took forever, and it was really awful, and it was just a waste of time. So I asked one of my friends, Oliver Galibert, who is a MAME dev, and he's like, all right, give me a few minutes. And he came back, and he's like, okay, I did it for you. So I was like, okay, well, that's great. Thanks for doing it. It works great. But how did you do that? Because I want to learn that way I can do it. And his only answer was just years of experience. There's really no process. You just got to know what it's like. Doing this with arcade ROMs over and over and over, he just got a knack for it. So if there's any lessons we learned, it's just have a lot of friends. And this is what the result was. We had the ability to decode data off of the ROM, but also to arbitrarily create our own images and then flash it back on, and then we got arbitrary control over the LCD. So cool, we got the image data down. What about the audio data? Can we craft arbitrary audio too? Because that would be really cool. We can make the Furby say provocative things, or I'm not sure Hasbro would be too happy about that, but. So I looked at the records. I extracted the actual data portion of the record after the size, and I tried pretty much every format, every codec that I could think of, and asked around, and I asked everybody to think of all the formats and codecs that they could think of, and nothing worked. It produced no reasonable, valid output. It was just static for the ones that even parsed it. And we still have no idea what format this audio data is. But one thing that we realized is that every single record started with 2 bytes. It's OX80 and OX3E. So I looked online, I was like, okay, maybe this is some sort of signature for this type of data, and I still got no results. So in order to actually figure out what this is, it'd be nice to look at the code that actually operated on the data, and from there we can make inferences about what the format actually is. So to this, we'll turn to the microcontroller. If we look at the microcontroller, which operates on the code, then maybe we can use this to gain better understanding over the data that it operates on. So look at the microcontroller, which is the big blob on the backside. But because we can't see it, we have no idea what it is. We have no idea what architecture it is, or what model it is, who makes it, or if it's even possible to recode off of it. So what I did was I traced pads to and from, and actually found that the ICE, SDA, and CLK pins actually trace directly to the microcontroller. So maybe it's possible to attach a debug probe on there, but at this point, each vendor sometimes has their own implementation of how that protocol works. So in order to actually move forward, I need to identify what this microcontroller is. So Googling the terms ICE data and ICE clock, I actually get exactly results for this company called General Plus. Not in any sort of technical documentation, but they're just like offhandedly mentioned on a couple pages in PDFs. So at this point, I wanted to get answers. I didn't want to guess anymore, and I turned to boiling everything in acid. If you've never heard of chip decapsulation, or better known as just chip decapping, basically what you're doing is at the center of every microchip is a die, and basically that is an integrated circuit that forms the logic or the memory or the main functionality or the functionality in general of what the chip is actually doing. What chip decapping does is actually exposes that, and there are a bunch of different ways to achieve that. You can do mechanical chip decapping, which is just take a pair of scissors and cut it and then try to break it off and hope you don't break the die in half. You can do thermal, which is putting it under a lighter and heating it up and hoping that the packaging explodes off and hoping that you don't kill the die in the process. Or you can be a little more proper about it and use really nasty chemicals to melt it off. And this is the most fun route and also the route that I went. Also, if you use chemicals, you can do live analysis, so that you can just decap the packaging on top of the chip itself and actually still leave it perfectly functional and intact. And then you can use that to inspect and even like instrument the chip while it's running. So different ways to do this. The first chemical that you can use is nitric acid, and there are different forms of nitric acid that you can use. The first one is concentrated, which is about 68% nitric acid, and the detriment of using this is that it requires like a high temperature, and it also degrades the bond pads in the process. Because the bond pads are made of copper, it will actually attack the copper while it's attacking the rest of the packaging around the chip. So what you're going to get is a bare die, and that's great for imaging, but that's really bad for live analysis. Or more professionals use fuming acid, which is 86% and higher, which will react at room temperature, but you probably still want to heat it up just to have the reaction show some sense of urgency. Also, it doesn't attack the copper as aggressively, and you can do live decapping with fuming. So nitric is really nasty stuff, and it really definitely requires a fume hood. If you look at the chemical equation, as it's attacking the copper, it actually produces nitrogen dioxide. And the beginning and end of that is that if you breathe that in, you're just going to be really unhappy. Also requires proper disposal. You need to handle it properly and dispose of it in proper hazmat locations. But the good thing is that it's actually pretty reasonable to obtain concentrated nitric acid. You can buy it from science stores, and believe it or not, you can get it off of Amazon as well. But the thing is that no one's really going to sell you fuming acid, although I've heard unverified reports that you can buy it on eBay. But if you do, you're probably just going to be put on a watch list, because nitric acid is one of the main ingredients in really aggressive explosives and fertilizer, and nobody wants to have that. The other chemical that's commonly used is sulfuric acid, and it's actually just commercial drain cleaner if you get it pure enough. The detriment to this is that it produces a really gross, disgusting black sludge, and when you're trying to recover the chip from it, you need to like fish it out, and it's just awful. But the good thing is that it does leave the bond wires intact, so it's actually really great for live decapping. But again, it's still nasty stuff. You still want to handle it correctly. So since I am a university student, I have access to cool things like proper chem labs, and I was able to actually go to the chem lab, and I asked to use nitric acid. So they let me use nitric acid, and I was able to use 70% concentrated, and I found that my best results came when I heated it to about 80 degrees Celsius. And it took anywhere from 5 to 60 minutes, and some of the chips even took a couple hours because in order to get the main microcontroller off and into the acid bath, it was chip on board in the middle of the board and not on a little desolderable one. So I actually had to take a pair of scissors and like cut the board in half and like cut a circle around it, and the acid spent a long time attacking just all of the debris around it. So once you actually fully decapped the chip, you need to recover it. And what you do is you just decant off the acid, and then you need to use a pair of soft tweezers to pull it out so that it doesn't scratch the chip. And there are plastic tweezers that are very commonly used by jewelers when they're handling expensive rocks. So what you want to do is when you're using nitric, you want to rinse it with deionized water first, and then acetone as a solvent to clean off any lingering epoxy or acid. But you don't want to do acetone directly after the acid, because solvents like acetone and ethanol react extremely aggressively with nitric acid, and if you're not careful, it will actually just burst into flames. What you can do is you can use deionized water and wash it off first and then use a solvent, or you can just try to submerge it with a lot of solvent at one time, so that even though it will be reacting slightly with the nitric acid, it will be so much solvent that the temperature won't be raised enough to hit the flash point. Also, if you're using acetone, don't use nail polish remover. What I like to say is it's 30% acetone and 70% bullshit. There's just a lot of additives in there that's just it's just not worth your time. And I actually found accidentally that ethanol works just as well as acetone. I was in the lab and I just grabbed a bottle of solvent and I just washed it off. And I was like, oh, thanks for letting me use the acetone. I was like, no, that's actually ethanol. So if you don't have any solvent, then just head down to your liquor store, and it works just as well. Great, so we covered our sample. Now we actually want to do imaging for reverse engineering of the integrated circuit. When you're going to use a microscope because they're really tiny integrated circuits, but what most people think of when they see a when they think of a microscope is a biomicroscope, where you have your sample between slides and then a lamp shines from the bottom. But you can't do that because your sample is going to be metal and it's not transparent like slides are with organic matter in it. So what you need to do is actually need to have specialized microscopes that provide illumination from the top. So this could be stereo microscopes, which provide illumination from both sides and you just don't care about the lamp on the bottom. It could be an inverted microscope, which actually holds your sample upside down and shoots the light from the bottom. Or it could be a metallurgical microscope, which provides illumination from the top and is actually meant for working with metal samples. What I found, and a lot of my friends actually like to use, is I use an Olympus BH series microscope, and it's actually really cheap compared to most other microscopes there. It's sub $500 if you get it used, and it provides really great images. The cool thing about using optical imaging is that you're actually shooting light at it, so you can see through the empty space in the layers. You actually see the lower metal layers and components underneath. When you actually want to do imaging of it and take digital images and capture them to your computer, you need to get a trinocular head for your microscope and then place a camera on top. But the image quality is going to be very highly dependent not only on the camera, but also on the quality of your objectives as well. I didn't have a really great microscope, so I got to work with what you got. If not really sure what you're looking at here, this is an old biomicroscope that I stole from my roommate. And I didn't have a trinocular scope, so I also stole my roommate's DSLR, pointed it down the lens, and because it didn't provide illumination from the top, I took a bunch of Android phones and scotch taped them around them with the flashlight app. And I was really impressed with how well it worked. So since then, I've since acquired an Olympus microscope, and everything's great, but those were the days. Another perk of working or being at a university is that you can use really expensive equipment there. So I talked to the bio department. It's like, hey, I want to use a SEM. And great, they set me up with a SEM. So I used a scanning electron microscope, and it provides really high resolution images at insane zoom levels. These are meant for working with small samples, and you can see the fine, micro details. One detriment of using a SEM is that it only produces black and white images, and also the fact that you can't see through the top layer. So you're only looking at the topography of the passivation layer on top of the chip, or in better terms, the glass layer of the chip that provides a barrier between the circuit and the contaminants in the package around it. So here's kind of a crappy image of the microcontroller that I decapped with a SEM, and you basically have to zoom in on each section and take individual pictures and then stitch them together afterwards. But if you actually zoom in, we see markings on the chip right below one of the bond pads, and we see there's this marking GFI 392, and that is the model number of the chip. Also on the left side, we see a serial number, or something, probably a serial number for the chip. So I Googled GFI 392, and there were really no results at all. So maybe it's just rebranded. Maybe Hasbro bought this chip and they put a different marking on that, their own internal marking. So this is probably some other company's chip, because I don't think Hasbro has any semiconductor fabrication factories anywhere, of their own at least. But I did find one site that had a hit for this, and there's a company called Chipworks that provides commercial decapping and analysis services. And in one of their blog posts for Halloween, they actually decapped the Furby and a couple other toys, and they provided a little sample of one of their images. And we see that they actually found it too. But interestingly enough, there is no serial number on their image to the left of the bond pad. So what this leads us to believe is that there are probably multiple revisions of the same chip. But we still don't really know what this chip is, and we want to find out. So thinking back, we remember ICE data and clock that go into the chip, and we found that they directly correlated to this company called General Plus. So maybe General Plus made this chip. So we Google it, and we find that it's a company in China, and they mass-produce low-cost integrated circuits. And they're commonly found in video games. I believe that there's a group that did Wii hacking, like Nintendo Wii, and they found a bunch of knockoff Wii games, and they actually all had General Plus chips in them. And as well, in previous years, Natalie Savanovich did a lot of reverse engineering and hacking of the Tamagotchi toys, and she found that they all had General Plus chips as well. So I followed the same process that Natalie used to identify the chips after she decapped them from the Tamagotchi. I just went on the General Plus site, and I just browsed data sheets one after another until I found one that had exactly the same bonding pad layout as the one on my chip. Awesome. So we find from this that our microcontroller is a GPL 169-256A, and it's a 16-bit microcontroller running a proprietary General Plus architecture called Micro NSP. Great. It's also an LCD controller, which makes sense. It drives the LCD screen, which is mounted directly on top of it. And it also has a 256 kilobyte mask ROM. So that's probably its internal ROM where it stores its code, and it's also read-only. Also, there are references in the data sheet to ICE, which is a debug port, and that's cool. But in order to interface with General Plus's ICE interface, you have to use a General Plus debug probe, and you attach to it, and then you can use that for programming functions and for verifying the data that's on the chip, as well as doing debugging as well. So at this point, I put on my social engineering hat, and I emailed General Plus, like, hey, so I'm a university student, and I'm doing a class on microcontroller stuff, and I wanted to know if I could get a debug probe so that I can show this demo to my class. And they sent back an email and said, well, you're going to have to provide a little more information than that. So I went on and I actually said, okay, well, it's a GPL 169-256A. And I said, okay, well, I want to make sure that the code on the Furby, I want to verify the code on the Furby as a demo for how you can interface with components like this. So then the representative responded, well, we don't have a any sort of policy for dealing with universities and other educational institutions. So we're sorry, we can't give you a debug probe. But we'd be happy to forward you to the Furby department in Hasbro. So they forwarded me to the Furby department in Hasbro, and I talked to the head of the Furby department, and the guy said, "Oh yeah, that's awesome. I saw your blog post in December. Everybody really likes it. So let me talk to some guys, and we'll try to get you a debug probe." I'm like, cool. So a couple days later, I get an email back, and it said, "Hey, so we really want to get this to you, but our lawyer said no. So we're really sorry, but if you want to work on this stuff, we'd be happy to provide you with an internship at our Providence office if you want to come work for Hasbro." So then I was like, okay, cool. And then the lady from General Plus then responded to the thread and said, "Yes, come work with us. We can make money and happy at the same time." So anyways, that was a dead end. And also, like, it's semi-reasonable that the actual debug port was disabled at production. It's usually not, but there was an option in the confirmation sheet that said, "Did you enable the ROM protect bit?" So unless we're actually like manipulating the chip, it may not be possible to actually interface with it over ICE. There was, I also tried to just see, there was a test pin as well, and I tried pulling that high, I tried pulling it low and manipulating that. And I put logic analyzer probes on the clock and data, and I didn't see any activity on there. So it might be disabled. But the cool thing that we find, just knowing what the chip is, we look in the data sheet, and it has a section on audio algorithms that the microcontroller supports. So all of these algorithms, just Google everything, and eventually I find, or it is found that there was a GitHub repo that had a couple of these algorithms with some amount of source code, but mostly header files, and also some actual samples of each of audio files that were encoded with the algorithm, as well as the compiled implementation in micro NSP of the algorithm, but not the source code. So the fact that we didn't have source code kind of sucked, but looking at all of the different encoded audio files, it's actually found that one of the audio files had the exact same OX80, OX3E header on it. And from this, we can match the byte pattern and find that the audio algorithm used by the Furby is SACM DVR 1800. So at this point, we still have we don't have source code, but we have these compiled libraries with the implementation of it, but it's in micro NSP, and that's really crappy to debug or to disassemble and reverse engineer it. So first off, the first hurdle was that these libraries are in this proprietary format, in this proprietary General Plus format, and I didn't really know how to like reverse it and figure out its format. So I talked to my friend David Carney, and he was able to reverse it in a couple days. And he also made an IDA loader for it. So now IDA supports, at least unofficially, it supports being able to load micro NSP and General Plus libraries. If you want to download it, it's up there on GitHub, and that was really cool. But moving on, we have we looked at decap the other chips, and the small chip on the left of the mask ROM was actually this General Plus audio driver, and all it does is just provides amplification, and it's not really that interesting in the general reversing of the Furby. But this image was taken with an optical microscope compared to a SEM, so you actually get all sorts of extra data, such as you could see actual color differences between the components and the layers. And you can kind of see down to the lower layers as well. But now we come to the daughter board, and we find that there's this chip. And we decap that one, but we don't really know what that is. It has the marking GHH 393. But I looked through all of the data sheets on the General Plus site, and I couldn't match the pad layout to anything that was in the data sheets. But again, it's still likely General Plus, just because even just like the font that's on the markings matches to everything else. And some of the components look similar. But we don't know what this chip is. Is it a microcontroller? It could be because it has an internal clock and is also connected to peripherals. Or is it some sort of just really smart memory chip? Because it has absolutely huge memory banks on it. And there's really not that much logic compared to the main microcontroller. The main microcontroller had huge memory banks on it too, but it was still overwhelmingly just logic and transistors. But this is overwhelmingly memory bank, so there's really not that much in the way of, it's hard to believe that it would be a really smart microcontroller. So in order to answer some questions about what this is, I then got some help and proceeded to delayer the chip itself. And delayering is actually going to be the process of taking the layers of the microchip off one by one and then imaging it to see where the different interconnects are out to, and also see what kind of components underneath. So in order to achieve this, we used hydrofluoric acid at 3%. Hydrofluoric is also really awful and might be worse than nitric, or it is worse than nitric and sulfuric, because when it gets on your skin, you don't realize it's there until your bones start decomposing the next day, and it's just terrible because it attacks calcium. But you can buy hydrofluoric acid as commercial rust remover, and the main way it works is just you apply it and then it takes off the top layer of whatever it's attacking. So you can use it to clean rust off of metal just by taking a layer of the metal off one by one. You can use it to clean lab equipment by taking the top layer of the glass off, like micron by micron, or you can use it to delayer integrated circuits. So what we did was we got a small vial of hydrofluoric acid, 3%. We put the chip in there, and we heated it at and then we took that and then put it in a water bath. And what that did was it limited the temperature to 100 degrees Celsius to make sure that it didn't waste acid and also make the reaction move too quickly. And we put it in for intervals for 1.5 minutes at a piece, because what you're doing is you're going to let it react with the chip, and then you're going to take it out and put it under a microscope and check to see if you have the result that you want. And if you need to let it continue taking off the layer, you put it back in for another minute and take it out until you actually have the entire layer off. So what this basically did was it first removed the overglass layer off the integrated circuit, and then it started attacking the aluminum in the metal layers. And what that would do is it would weaken the connections between the different metal plates, and then you would see them float away. And that was really cool to see. And by looking at the actual chip itself and delayering it, we find that the chip has a substrate, which is silicon wafer. It has a poly layer, and then it's a one metal process. So there's only one layer of metal interconnects between the components. And at this point, we'll actually go quite a bit deeper into this, and I will channel my inner Chris Tarnowski, and I'll try to do a close-up analysis of the chip itself. So here we have an image of the top metal in this daughter board chip. And we can see all the same features that we saw on the slide. But the first thing that we're going to look at is actually this top left here, where we actually see rev markings. And we'll get a better picture just by looking at a 40x picture of this. And what this is these are actually like comments in source code, but this provides a little bit of information about what layers are on the chip. And we see here that on the far right, there's a kind of a muted color, and that corresponds to the active layer, which is the lowest level, the lowest layer in the chip, and is actually where the silicon substrate is. The chip is built on top of it. Directly on top of that, there's always a poly layer, which provides the gate connects to the transistors, where source and drain are actually located in the substrate. And then the next one, 56Z, is or 56N. You can zoom in on that and actually see that it's kind of hollowed out, and you don't really see any sort of like color on the inside. And if you look really closely, you can see dots within there. And what that tells us is that this is a via layer, where it actually provides vias between the metal layer, and then the poly beneath it. And then over here, we see a red rev marking, which corresponds to the top metal layer. And you can see that's the same color as the metal around it. And then this over here is the rev marking for the overglass, which is actually the passivation layer that protects the chip from the outside world. So now that we kind of know how many layers are in the chip and what we're working with, we want to start actually looking at the other components on the chip and actually start reverse engineering the contents of it. So we look around and we see this big structure here, and we see a bunch of memory cells. And if you compare this to other components, we find that this is called SRAM. And basically, we can count the number of cells that are in here and by the number of rows. And then we can get an accurate guess, or a very accurate, educated guess about the actual SRAM capacity of the chip. And if we're trying to match it against other chips or other like data sheets where we don't have the actual pad layout to match against, then we can compare the specifications that we find within the chip and then match it against the data sheet. So the fact that there's SRAM, also the fact that there is SRAM in here could mean one of two things. It could be that it's internal memory to a microcontroller, or it also could be used in a memory chip for write buffering. So this doesn't really answer our questions, but it's good to note that it's there. And then we look here at the really big memory banks here, and we want to count to see how big this is. So we find by zooming in and actually counting the cells in here, or the lines, we find that there are 32 columns and 128 rows. And if we make the assumption that there are 32 bits per word, and each of these row by column is a word, then there are 8K words times 32 bits, which equals 32 kilobytes of memory total. So again, more information for when we actually start looking at data sheets. So again, the fact that these are huge memory banks could mean that it's a really dumb microcontroller or it's just a really smart memory chip. We're still not sure. Zooming in down here, we see a component, or a series of components. This is a really big resistor, and this is a series of capacitors. And what this produces is a component called an RC oscillator. And an RC oscillator produces a sine wave. And when you want to, an RC oscillator is actually used internally for generating a clock signal. So we have this sine wave, and now you're going to pitch that against a comparator. So you have a comparator at 50%, and then every time it goes above, it sends a 1, and every time it goes below, it sends a 0. So now you have a perfect square wave coming out of it. But if you want to reduce the amount of noise, you wouldn't use a comparator specifically, but you would use a Schmidt trigger, which is basically a comparator that on the upswing, it raises the threshold, and on the downswing, it lowers the threshold. So the fact that there's an RC oscillator in here means that there is an internal clock signal, which is a really good vote for the fact that it is a microcontroller. Although it's not unheard of that internal clock signals are used for non-microcontrollers as well. Also, RC oscillators are really, really low quality clock signals as well. Every time you produce one, it's slightly different, and it also slightly changes the frequency at which it outputs. So if you have two RC oscillators next to each other, they're not going to be outputting at exactly the same frequency, although it's close enough to get the job done. Also, the fact that it's low quality means that it's highly influenced by temperature and voltage. So any fluctuation in temperature or the input voltage is going to also affect the output of the sine wave and clock signal. So this would facilitate glitching if we ever wanted to do that. We can just heat it up, and then it would actually affect the execution of the chip if it is a microcontroller. So at this point, we then continue to delayer the chip, and we put it in HF and attack the overglass and the top layer, and then now we're looking at the poly layer. So now we zoom in, And what we see is that in the memory banks, we actually don't see any bits. If it's a masked ROM, you would likely see actual discrete bits corresponding to 1 and 0. But we don't see this here. But that doesn't mean that it's not masked ROM, because there could be bits in the active layer as well. But usually when you're trying to reverse out masked ROM optically, there are 3 most common types of masked ROM: via masked ROM, metal masked ROM, and implant masked ROM. So via masked ROM will actually have transistors with every possible bit location, and then have a via shorting it out to which corresponds to a 1 or a 0 if there is an absence of a via there. A metal masked ROM will actually have the short completely within the metal layer. So wherever there's a transistor, then you're going to have a metal routing around it, so it always allows current through. That will correspond to a 1 or a 0 depending on the type of ROM that it is. Also, implant masked ROM, the transistor is always there, regardless if it's a 1 or a 0, but the fabrication process of the transistor raises the voltage threshold or lowers the voltage threshold such that it's always turned on or always turned off, and then that corresponds to a 1 or a 0. Also, it's not unheard of that there are also a thing called active masked ROM, and basically once you get down to the active layer, the 1 or a 0 is related to whether or not there is a transistor there or the absence of the transistor. So the fact that we didn't see any vias and the fact that we didn't see any metal shorts means that it's not a metal and it's not a via masked ROM. So this means that it could probably be an implant masked ROM, or it could be an active. So now we want to go down to active. And you can see now we're at the silicon substrate of the chip. And you don't really see components, you just see the outlines of them where they were fabricated and implemented on top of. But now we're looking here, and there's absolutely nothing where the memory banks are supposed to be. And this is actually really confusing, because usually when you have a masked ROM or any type of memory at all, you are going to have transistors or some sort of memory cells in every location. Whether or not you can actually read them out optically is up to the implementation, but usually there's something there. And we find that we just don't see anything. So the fact that we don't see any transistors anywhere means that it's not active masked ROM, but it still could possibly be an implant masked ROM, such that we just can't see the transistors optically. So what this means is there are a couple of ways forward. We can just assume that it could be something else like flash memory and it's writable, but it's probably the fact that we don't see any memory cells means that we still have like more questions than we have answered. Also, if we want to keep going with the assumption that it's implant masked ROM, at this point we can use a technique called dash etching, which is actually then submerging it with further chemicals. And what that will do is then it will create shadowing around the transistors that have like either a higher or a lower voltage threshold, and it will not have shadowing around the ones that are either like 1 or 0. So then you can put it under a microscope or a SEM and then actually visually see where the 1s and 0s are. So at this point, I went back and actually continued fully tracing all of the traces from the chip to pads and other components. And I actually found that there was a pad called VPP, which is voltage programming pin. So the fact that there's a VPP pin there could possibly mean that it is writable. And it's possible to apply voltage there, and then you have the ability to reflash the chip with your own contents. But again, without actually knowing exactly what the chip is, we are not sure what the purpose of that pin is for. Also, we were able to trace out the fact that there are 0 through 7 pins labeled IO-C. So they could be an 8-bit I/O port, which gives another vote for the fact that it is a microcontroller, not just a dumb, it gives a vote for the fact that it's a dumb microcontroller, not a smart memory chip. So looking back on the General Plus site, we find that besides the micro NSP microcontrollers. General Plus also produces 8051 and 6502 microcontrollers, which kind of fits the profile. And they're like really dumb, not very complex 8-bit microcontrollers. But the fact is that they don't have data sheets for most of their products in that line, or the few data sheets that they have don't have the pad layout. So it's really hard to say with precision, exactly what that chip is. So at this point, we're still have some answers that we need, and that's where I am in the project right now. So to do, I still need to extract the ROM from the daughter board microcontroller, and it would be great to explore the programming related pads, because it would be great to be able to read it off and just write back to it, because then you get code execution and it's easy peasy. Also, extracting the ROM from the main microcontroller would be great, because that would be like the main firmware that actually drives the Furby. And the different ways that we can get that, we know that there's a mask ROM in there because the datasheet says so. So if we delayer it, it's almost certain that we're going to be able to read out the bits in some way or another optically. Also, it might be possible to get code execution either through power glitching or some sort of clock glitching by affecting the environment. Also, the fact that we have control over the data ROM, where the image and audio data is, we might be able to futz with that and then fuzz the memory chip or get some kind of memory corruption. But then we're getting into the land of blind exploitation on an unknown architecture, and it's just really, it would be a really interesting time. Also, actually being able to fully decode the audio data, we identified what it is, but I didn't actually go forward and reverse engineer the code itself, just because there were other things to work on. But that there is a way forward to actually be able to reflash the Furby with arbitrary audio and have it say funny things, but it's just a tedious process. Also, if we actually get the firmware off and we're able to load the code into IDA, the fact that it has remote communication is really awesome, because then we can have Furby zero-day exploits. And my grand goal for this project is to have an exploit to basically get code execution on a Furby through its audio protocol, and then worm that through other Furbies so that they all are exploited one after another, and then world domination, et cetera, et cetera. Everything I've done so far is up on GitHub. You can get it there. There's also, the link is on my site. Thanks to everyone who helped me, all my friends and all my professors who provided me with analysis and resources and support, and especially to the site siliconprawn.org. Thanks. Any questions? The question was, how long have I been working on this? I've been working on it since probably October or November of 2013. Off and on, I haven't done it entirely through, but since then, at least. Yes?
How many Furbies were harmed in the making of this presentation?
So how many Furbies were harmed in making this presentation? Surprisingly, only 3. And it's great because friends just keep giving them to me, so they're kind of expensive. Do I need more Furbies? I'm not going to say no. Yes? Okay, so the question was, how often do Furby refreshes occur, and will the work become obsolete? So it's actually kind of interesting, because the Furbies came out originally at the end of '99 and like early thousands, and then nothing happened for 10 years, and then they just made the new ones. So I actually looked at the 2012 just because that was the first one that was given to me, but there is a new revision called the Furby Boom, which actually isn't really that different. I haven't looked at it, but I don't expect it to be very different. There's no reason for them to change anything, and it would be very surprising if they had different components. The fact that it's a different version means that it'll be like a slightly different implementation, but I think all the same stuff still applies. Thanks, guys.